question number 4. All right, so evaluate the definite integral of f of x equals x cubed from interval -1 and 1. Okay, so they, in the original question, they asked us to use a limit definition of the integral. And so they want us to calculate the integral of x cubed dx. But this notation here, this integral notation from 1, is actually this notation, this integral notation is actually a notation for this entire equation, which is a sum rule or a sum function. Okay, so we have the limit as n approaches to infinity. Oops, that's not infinity. Of the sum from n to I equals 1 of f of ci times delta xi. Okay, so this notation here is basically covers for this formula here, which calculates the limit of the sum function of the function as ci times delta xi. So what is ci and delta xi? So ci is calculated by the right-hand values, and I'll get into what this all means. Okay, and delta xi equals b minus a divided by n. Okay, so where does all this come from, right? So what does the integral calculate? So the integral calculates the area under a curve, right? So many mathematicians were trying to approximate and calculate areas under the curve because they found that is very significant to many different calculations. So what they devised was that they would calculate the sum of multiple rectangles under the curve, and that would help to approximate the area under the curve. So let me explain here. So if I were to zoom out here, all right, so I'm going to put my illustration here. Okay, so let's say that we have a simple line function. Okay, so let's draw the line. I don't want to. Okay, so let's draw out a line here. Let's just say it's like goes through the origin. Okay. All right, so this is our line. I don't know what the line equation is, but we're just going to call this f of x. So what they devised was to calculate the sum of same length rectangles under the curve. And how they did that was, so they wanted to say, okay, first we need to define an interval where we want to calculate under the curve, right? There's interval from here to here. So they said, oh, let's make the interval from A to B. Okay, so let's say the origin is A, and this top part over here is B. So they wanted to calculate the area under this curve. Okay, so they said, okay, so let's calculate using rectangles, and let's add together, let's say, 4 rectangles. Okay, so they want to have 4 subintervals, and they want to calculate the sum of those rectangles. Okay, so if we were to split this up into 4 equal rectangles with similar lengths, right, we'd have 1, 2, 3, right? So we have 1, 2, 3, 4, and they will calculate the area of each of these rectangles, and they will calculate, oops, and then they will try to approximate the area under the curve using that. Okay. So I'm going to just draw these rectangles for now. And why I'm drawing it like this is because there are 2 widths, I guess. So they considered this to be the length first. So let me describe that. So the length of these rectangles are all similar. And if we're to bring one of these lengths down like this, the length would be calculated as delta xi, okay, which is basically the difference between these intervals divided by the amount of rectangles that they want to have. So in this case, they wanted 4. So by having a difference between the intervals and dividing it by 4, they were able to find rectangles of similar lengths, right? And so now all you really need to do is calculate the height of these rectangles, or the width, right? So by calculating the width of these rectangles, they were able to calculate the area by multiplying the length, the equal lengths, plus the width. So they had 2 points to choose from, right? Were we to choose from the left side or the right side? And you can choose from either, okay? So it is a known fact, I won't get into this too much, but the left side will underestimates the area, and the right value, or the right side, will overestimate the area under the curve. As you see here, if we use the right-hand side values for the height, we would see that there are some part of the rectangle that's overlapping over the curve. Okay, so CI is basically, we can use the left-hand side or the right-hand side. Here in the notation, we use the right-hand side, right? So we started out at the beginning of our interval, and we added the first length of the rectangle here, right? So if I was to equal 1, then C1 would equal the beginning of our interval plus the length. So we'll end up on the right-hand side, as you can see here, right? So the length is calculated by A plus B minus A divided by N times I, right? So if we have 4 rectangles, then we'll have C1, C2, C3, and C4, right? And these will correspond, we'll plug it into our function, and we'll find our height of the function at that point. And by doing so, we can calculate the rectangles, and then we use the sum function to add up all these rectangles together to estimate the area. Okay, so now what I said before is that the right-hand sum, as you can see here, overestimates the area, while the left-hand sum underestimates. Well, they're able to come to a very, very good approximation of the area under the curve if we continue to add more rectangles together. So if we were to increase the amount of rectangles we wanted to add together, the area overlapping over the curve will continue to decrease, right? So then they wondered, what if we set the limit of this function to be heading towards infinity? What if we had infinite rectangles to add together? Then the area will be almost perfect and corresponding to the area under the curve, actually. So that's what they wanted to do. And that's where the integral came from. So this integral notation is actually representing the limit of the sum function of the areas of rectangles. Okay? And by doing so, they come to a very good approximation and actually perfect calculation of the area under the curve. So this is what the limit definition of an integral is, and this is the notation for it. Okay. So now that we've gotten that out of the way, we're going to calculate the definite integral of x cubed in terms of dx. All right. So let me zoom back in here, and let me drop. So I'm not going to use a limit definition anymore. We're just going to calculate the definite integral. Okay, so first thing that we need to use is that we need to use the integral, the power rule of integration, right? Which states that integral of a power function is just the division of the power function with exponent plus 1 divided by set exponent plus 1 plus constant c. So we're going to use that. In a definite integral, you don't need to include a constant c because we're actually just going to be subtracting that out, and I'll show you guys explicitly what I mean. Okay, so if we were to calculate the integral of this, from 1 to -1 of x cubed dx, we would calculate, we'll use the power rule, and using the power rule, we know that it's x to the power 3 plus 1 divided by exponent 3 plus 1 plus c. Okay, so let's do this now. So this is the, whoops, let me just simplify this. Okay, so we would have x to the power of 4 divided by 4 plus c from 1 to -1, okay? And if we were to calculate this, right, so we would plug 1 into here and subtract it by x to the power of 4 of -1, okay? So we would have 1 to the power of 4 divided by 4 plus c minus -1 to the power of 4 divided by 4 plus c. Okay. All right, so if we were to calculate this, we would see here that we have 1 over 4 plus c minus, so the -1 to the power of 4 is -1 times -1 times -1 times -1, so it's +1, so it's 1 over 4 plus, or minus c. So we see here that the c's cancel out. So that's why you don't need to include a c with a definite integral, because your assumed constant will cancel out. And all we have left is 1 over 4 minus 1 over 4. Okay? And we have that equal to 0. All right? So that's the area under the curve between 1 to -1 of the function x cubed. So this is a cubic function, right? So if you were to actually wanting to find the bounded area under the curve, because this equation does not consider the fact that might be negative areas. So any area below the x-axis will be a negative area. And if we were to graph this cubic function out, we would see here that it's perfectly symmetrical. Let me just graph it out here and show you guys what the cubic function looks like. So the cubic function kind of looks like this, with a saddle point and it inflects to the below, right? So if we were to calculate the area from, let's say, -1 to 1, we would see here that the areas would, so if this is 1 and this is -1, we'd see here that the areas would cancel out because the integral does not consider negative areas to be, well, the integral basically considers negative areas. So if we're adding this together, we'll get 0 basically because they cancel each other out. So if you actually wanted to calculate the area under the curve without considering negative areas, you would just multiply the integral of from 1 to 0 by 2. By doing so, you would bypass the negative area, and you would just need to multiply this because you know that this area and this area are the same. They're just negative and positive, right? So that's what the junior tutor suggested instead. But that's the definite integral of the function x cubed from -1 to 1, which is just 0. Okay, so the solution is correct.